Let me just get this recording thing going. There you go. So today, I first want to say is that just the other day, I gave our fourth year students, I gave a presentation on how to give a presentation. And then I told them, I don't think I do half of the stuff that I tell them to do. But one of the things that I've been thinking about for quite a while now is what I told them is you should always think about what you want people to take away from your talk. And I've been mulling about this talk for a while. And I think after today, if you just understand what the localization game is and share a little bit of excitement for it with me, then I think I would have done my job tonight. So I'm going to give you a very short introduction to the localization game and how it's played, and then I really want to make sure that we understand how the game works. So I'll look at a proper example. We'll do some general results, and I'm really just going to focus on the very basic results today. And then after that, look at specific graph classes, more specifically at trees, and then also on outer planar graphs slightly, and then unicyclic graphs. And I'll end up off with some open questions. And I heard this topic at a conference in Poland quite a few years back and found it very interesting. It took me a while to get students on board so that we can start with this project. And you will see in the open questions section that there's quite a lot of things that can still be done. And maybe I can tempt you to join this search for answers in the localization game. Okay, so the localization game is kind of a cops and robbers game. So it's a two-player game where the aim of the game is for the cop to locate the robber. So how it works is the robber initially starts on the graph at any position in this graph. And the cop obviously doesn't know where the robber is, because if he knows where the robber is, then the game is done. So it is unknown to the cop. Then for the first step, the cop is allowed to probe k vertices in this graph. And with that, I mean he can ask the distance of the robber to k vertices in that graph. With this information, so when he receives these distances, he can then determine whether he can locate the robber. So it might be that these distances immediately locates the robber, and then the cop wins and he can escape this loop. But it's possible that that doesn't happen. So if it doesn't happen, the robber is allowed to move. So the robber is trying to get away from the cop, so he's going to run somewhere or stay put if it's a good hiding place. But he can only move to his closed neighborhood. So he can't jump to a node on the other side of the graph. He must stay in his neighborhood. After the robber has moved, the cop is allowed to probe again. Now, the cop is not restricted to the structure of the graph. And the way you can see this as a cop sitting in his office, and he is just pushing buttons on his computer, like a high-level technical cop. And he can probe wherever he likes. He doesn't have to be constricted to the structure of this graph. And this process continues until either the cop can locate the robber. He doesn't have to occupy the same vertex as the robber. He can just know where the robber is. Or if the robber can evade the cop forever, then we say that the robber wins. And what we are interested in this game is in the localization number. That is the minimum number of probes that the cop needs to do in every single step in order for it to win in a finite number of steps. Okay, so it doesn't matter what the robber do. This must cater for all possible moves for the robber. And with K, if K is the minimum number of probes, the cop needs to win in K steps. So for all of this to make perfectly sense, we are going to try and play this game on the complete bipartite graph K34. Okay, so we want to determine the localization number. And we are going to start by showing that 2 cops will not be enough. So we could start at 1, but then we'll just have to continue to 2. So we'll rather start here with just 2 of them. So I did not indicate all possible choices for two COPs. And the reason for that is that if we probe in the same partite set, things becomes really easy. So we're going to skip that part. But I promise you, it still loops. So for this complete bipartite graph, the gray vertices will be the vertices that the COP probe. Now you can see that we don't indicate where the robber is because we have no idea where the robber is. So the COP probes these two gray vertices, and then we look at what happens in this graph. So which vertices have the same distance to these two probe vertices? And you can, if you look at the red vertices at the top, you can see that they will all have the same distance to these two probe vertices. For the one in the bottom partite set, it will have distance 1. And for the one in the top partite set, it will be distance 2. So if you look at that distance vector, it would be 1, 2, if it's bottom, top first. And then the green ones will also have the same distance away from these two gray vertices. Now, when this happens, that we have a set of vertices where the robber can be safe, because we don't know and which of those vertices the robber is when we get that distance, we call that a safe set. Okay, so the robber can be safe on those vertices if all of the vertices have the same distance to the probe vertices. So if we probe one vertex at the top, one at the bottom, we get two safe sets. Now, say, for example, after the probe, the answer we get is that it is in the red subset. So we know that the robber would be somewhere here in the red vertices. Then we go to the next block. So if it's red, then what happens? Well, since the robber can only be here at the top 3 red vertices, like in this first case, it can only move to this shaded area. It can never go back to this white vertex over here. So now we only have to consider the shaded area. If we now probe again 2 vertices, you can see we decrease the red safe set, but the green safe set stays the same. So if the robber is on the green set, we go back to the first step because it's the same as that one. So we'll have to consider that at a later stage. If it is located to the red set, we continue to the next block. Now the robber has a new restricted area that he can move in. He can only move in the shaded area because it's located at the red ones. It can only move to the bottom or stay put where it is. There's all the possibilities where it can be. We again probe the 2 vertices, one in each set. Now the red vertex is uniquely determined. So if it's in the red set, then we know where the robber is. But still, the green set looks exactly the same as the first one. So then we just loop back to the first set again. So in this path, we can never solve for the green safe set. So now let's see what happens if we have a green safe set. So if it's at the green one, we go down to this block here at the bottom, and we see that the shaded area will be where the robber can move to. If we now probe these 2 vertices, one in each set, then we do find it in the green safe set, or possibly, but we can't find the robber in the red set. The red set, in fact, looks exactly the same as in the first step. So we go back to square one. So it shows that it doesn't matter where we probe, we can never find the robber. The robber will always be able to hide somewhere. There's a slight thing that you have to understand here, that it is possible that in some scenario that you can find the robber. So you can accidentally probe the vertex where the robber is, and you will get a 0 and you know it's there. But we have to cover all possibilities, which means that if he can hide, then we haven't won yet, because the robber might have a man in the inside and he will be able to know and predict our moves. Okay. So we definitely know that 2 vertices will not be enough. So now let's see if we can do this with 3 vertices. Now for 3 vertices, once again, we will not probe everything in one partite set. The reason for that is then we have a safe set containing all the vertices of the other partite set, and the robber can be anywhere in the next step again. So we're back to square one. So we probe at least one in the one set and at least one in the other set. So now you can see that we have one green vertex. It's already identified. So if a robber is on a green vertex, we catch him. If the robber is on the red vertices, we don't immediately know where it is and we have to continue. So in the next step, the robber can be anywhere in the shaded area. We now move our top probe just into that shaded area. And therefore we decrease the safe set. So there's less vertices where the robber can be. But he can still hide. On this point, it's just funny. I always refer to the robber as he, but in literature, the robber is always a she. But I can't get myself to say that. Anyway, so he can still be here. And then in the last step, there's a shaded area where the robber can be. But now if you probe 3 vertices inside that shaded area, then you can see we can uniquely define or identify any vertex in the shaded area and the robber is caught. Okay, so 3 is definitely enough, which shows that the localization number is equal to 3. So now I hope you have a better idea.
Yeah, a quick question, Riana. So what happens if you place 2 gray nodes on the top and 1 on the bottom? Does that change the game?
So 2 gray nodes at the top and 1 at the bottom?
Yes.
Quickly want to think you might play a little bit longer, or it might not work at all. Okay. Because in order for the cop to win, you just need one strategy that will cause the robber to be caught in the end. So it doesn't really matter if another strategy doesn't work.
I see. Okay. Yeah, you only need a strategy to corner the robbers. Yeah. Yes,
exactly.
Yeah. Thank you.
Pleasure. You are more than welcome to stop me in between. Yeah. So where I want to go from here is to give you some idea about bounds on this parameter. And this first one actually comes from where the game actually comes from. So if you know about cops and robber games on graphs, you might think that this originated from the original cops and robber game, but it did not. This game actually comes from the idea of a metric dimension of a graph. Now, the metric dimension of a graph is the minimum cardinality of a resolving set. And a resolving set is a subset of the vertices that such that every vertex is uniquely defined by the distances to S. So if you listen to that definition, you can maybe already see the link to the localization game. Because in the localization game, we want to catch the robber. And if every vertex is uniquely determined by the distances, we immediately will know where the robber is. So there's the link between the metric dimension and the localization game. And how the localization game then developed was to ask, but what if I don't use all these vertices in the resolving set at once? What if I use them one by one? Will I then also be able to uniquely determine the vertices in the end? And that's where it started. But then this brings us a very nice upper bound to the localization number. But just to make sure that we get what a resolving set is, if we go back to our K34 example, we saw in the previous 2 slides that if I only probe 2 vertices, that I will have safe sets. So I will have vertices that have the same distance to those probed vertices, or the gray ones. Even if I have 3 vertices, I will, if I remember in our picture, we had these bottom ones, these in the corner to be gray, and the top ones, and the 3 top ones were red. So we also had 3 vertices with the same distance. So 3 is not enough. 4 isn't even enough. If we have the 4 on the left-hand side, then the 2 upper ones would be red and they will have the same distance. So we need at least 5 vertices in order for it to be a resolving set. And because 5 is enough, we know that the metric dimension of this complete bipartite graph is in fact 5. This shows us that the metric dimension can be different to the localization number because In the bounds on the localization number, we can see that the metric dimension will always be an upper bound, because as I said when I explained it, if you probe the resolving set S, then every single vertex will be uniquely defined. So you can immediately find the top in one step. But because in the localization game, we can play this over and over, it might be that we need less, because I can push it in a corner, the robber him, and then I can eventually catch him. There's obviously a very natural lower bound to the localization number of 1. I want to add here, so let's see if I can find my pen. No. That the upper bound for the metric dimension is n-1. Okay, so in general, the localization number is bounded between n-1 and 1. The question we might want to ask now is, how good is this bound? Can the localization number be equal to the metric dimension? And otherwise, how big can the difference between these two be? So I'm going to show you 2 graphs which illustrates these 2 questions. Firstly, if we look at a complete graph, we can show that the localization number of a complete graph and the metric dimension of a complete graph will be the same. It must be n-1. Okay, so how do we know that? For K5, let's say we just take, for the metric dimension first, 3 vertices into our resolving set. Let it be these 3 in the right corner at the bottom. So then we have these 2 vertices at the top that aren't chosen for the resolving set. But the 2 of them will have exactly the same distance from the 3 bottom vertices, because it's connected to everything. So we have to choose at least 4. If we choose 4 vertices, the 5th one will be on its own and it would be resolved. So for the metric dimension, we need n-1 vertices. What about the localization game? It's a very similar argument. Once again, if I probe these 3 vertices at the bottom, then the top 2 would be a safe set, which means that in the next turn, the robber can move to anywhere on the graph. And then we're back at square 1. So we're going to repeat and repeat, and the robber will evade the cop. So then for the localization game, we also need n-1 vertices per probe. So that's the one side. We can have equality.
Yeah, there's one question in the chat.
Yeah. Oh, sorry. Let me open the chat. Can't see the chat. No. Sorry, can you?
Yeah, let me read it.
Here I have it.
Yeah.
Now I have it. Thank you.
Okay.
Should the metric dimension of the one vertex graph be 0? No, it should be 1. So because the metric dimension is a subset of the vertices such that every vertex is uniquely defined. So you have to have a vertex. And then that vertex is uniquely defined by its distance to the chosen one. It's just 0. So it will, the metric dimension must also be greater or equal to 1. Okay. If there's a follow-up question, I can now see the chat, so I'll keep an eye on that as well. Okay, so now the second thing that I want to explain to you is that the difference between these 2 parameters can be as large as you want it to be. And we'll do that with a star. Now for a star, firstly, if we want to consider the metric dimension of a star, if I choose the center vertex of the star, then everything else will be the same distance away from that center. So that's not really going to help me. So it would be better if I want to choose the resolving set to choose some of the leaves. But if I choose just one leaf, then all the others will have the same distance away from that leaf, even if I choose the 2 of them. So I have to choose all but one of the leaves. There we go. In order to uniquely define or uniquely determine the distances to the set. This one is actually nicely written out. You can see that the center one is distance 1, 1, 1, 1, and the one leaf is 2, 2, 2. And whenever we leave out any of these, we will create two vertices with the same distance. So the metric dimension of a star is always one less than the number of leaves of that star. But now, the localization number of a star is 1. It's played similar to the game we played with the complete bipartite graph. So if we start with one vertex on one of the leaves, then we can see the robber can't be at the center because then we catch it. So it's somewhere here at one of the leaves. In the next turn, the robber can move to anywhere but our first probe vertex. So we're decreasing the size of the safe set again. And then we just move our probe to the next leaf, to the next leaf, to the next leaf, until we catch the robber, because the robber can never move over the center. So he can only stay where he first started. So then eventually we can catch the robber. Let me just see, there is maybe amend the definition to say non-empty subset from Jonathan. I will do so. Thank you, Jonathan. Oh, that was a direct message. Sorry, I just saw it afterwards. Okay. So this shows, if we calculate the metric dimension of a star and the localization of the star, that the difference between these two parameters can be as large as you want it to be. Okay, so even though we have this upper bound, it's not always the best. The next thing I wondered about when I was looking at these localization numbers was whether, so we know we can have n-1 for the localization number. We know we can have 1. So we go from, actually we should not take the star, but we can go from a path, very simple, which is 1. You just probe the one end of that path and then everything is uniquely determined. So we have localization number 1 for a path, localization number n-1 for a complete graph. What happens in between? Can we find a graph for which the localization number realizes every single one of these numbers in between? And we can. It looks kind of like a star with a blown up center. So if you contract these black vertices in the middle, you'll have a star. So in this graph, we have a complete graph on k nodes, which where k is the localization number in the center. And then to that, we attach n minus k isolated vertices and make them adjacent to everything, every single vertex in your complete graph. Now for this specific example, I'll just quickly explain to you why this is true. So we're looking at G95, so n is equal to 9, and it will have a localization number of 5. So if we probe 4 vertices, and all those 4 vertices belongs to the complete graph in the middle, then every single one of these vertices on the outside will have the same distance away from the 4 in the inside. They're all connected, all adjacent. So therefore, the outer vertices will form a safe set. And then what will happen in the next step? Well, the robber can be anywhere again. So it's not going to help us to just probe 4 in the center. What if we probe 4 on the outside? Well, same thing, then we have a safe set on all the vertices of the complete graph, and in the next step, the robber can be anywhere again. Same thing happens if we probe less than 4 vertices in the complete graph in the middle, then we'll have a safe set in the complete graph. Say, for example, we probe the bottom 3, like in our previous example, then the top 2 will be a safe set, but those 2 vertices are adjacent to everything in the graph. So then the robber can move anywhere he wants. So we know that 4 is definitely not enough. To show that 5 is enough, we follow the same idea as that of the localization game on a star. So we're going to probe 4 vertices, n-1, k-1, sorry, in the complete graph to make sure that all the vertices in the center complete graph is unique. So the robber can't be on the center, in the blown up center. And then we start probing these outer vertices one at a time to make sure that we catch the robber. So then 5 vertices will be enough. Okay. Now I think the next slide will be a surprise to me because I can't remember. I'm going to first stop here. So if you think about this, maybe it has crossed your mind already. If we look at the complete bipart, a complete graph, we will always need, for just a complete graph, we'll need n-1 to locate the robber. And in this nice example, we also need n-1 to make sure it stays there in the middle. So it would be really nice if we can get a result in terms of the click number. Think, for example, about colorings. We know that the chromatic number is always big or equal to the click number. Well, it would have been nice, but it isn't like that. Because if we look at the next example, you can see that this first graph, I call it the double house graph, contains K4 as a subgraph. So we would like to think that the localization number should be 3 for that one. But we can, in fact, locate the robber immediately with just 2 probes. If I probe the roofs of this graph, so if I probe V and the one that's not labeled, then every single vertex in this click would be uniquely identified. X would be 1, 1. This vertex here will be 1, 2, 2, 1, 2, 2. So we need less vertices than we need to in order to locate it on a click. So that is something interesting. We'll follow up with the next slide on how we can incorporate the click number into the localization number. The other thing that's interesting is that the localization number is not monotone on taking subgraphs. What that means is that it would feel natural that if I know the localization number of a graph and I take a subgraph of that graph and want to find the localization number, that the localization number should decrease. But that's not always the case. Because if I take away one of these roofs of these graphs, then I'm left with the house graph. And in this house graph, I need 3 vertices to locate the robber. So the removal of a vertex does not ensure that the localization number decreases. It might mean that it increases. So back to the click number. The result here gives us an idea of how we can use the click number. It's just not really good bound in terms of the localization number. This result is very similar to the one in terms of the metric dimension of a graph. And you would see this in many cases, that the extremal cases of the localization number coincide with that of the metric dimension. So our bounds sometimes coincide with the bounds of the metric dimension. So it says that the localization number must be bigger or equal to log 2 of the click number. I just thought I'll explain this quickly. I hope this picture works. So say we have this here in the block would be our click of size omega. And we say we probe K vertices, be here at the top. And these dotted lines does not mean they're adjacent to the click. It just means there's a path going to that click. So maybe it should be everywhere, but it's just to show that there's some adjacency. So for each of these probe vertices, the vertex in the click will either be at the shortest distance from that probe vertex to the click. Let's say the shortest distance is from that vertex to the click is D. So it would always either, be at distance D from the probe vertex, or it would be at distance D plus 1, because it's adjacent to, every vertex in the click is adjacent to a vertex at shortest distance from the probe vertex. So for each of these vertices in the click, we can either assign the value 0 if it's at distance D, or the value 1 if it's at distance D plus 1, for each probe vertex. So for each vertex in the click, we'll get a K tuple, which tells us whether it is as close as possible to the probe vertex or one away from that. And we can do this for everyone in this clique, which means there is a total of 2 to the power of k such tuples. So as long as the number of vertices in the clique is less than 2 to the power of k, the k probe vertices will immediately catch the robber. So therefore, our localization number will be bigger or equal to that of log 2 of the clique number. Okay. But this is normally a very small lower bound, and it only helps in graph classes where the localization number is really small. It has not aided me in anything, it's just interesting. Okay, but the reason why I was thinking about this is I would sometimes say the robber hide in a graph. So where he's safe, he hides there. But there's some structures, subclasses, subgraph structures where the robber can continuously hide. So he can be in one safe set and then he can just move around in this graph. So he can stay there forever. So I was hoping that the clique would be something like that, but it was not. It's just if there is, if it's really small in comparison to the probes. But there are some graphs where a robber can hide from a single cop. In 2012, they showed that if we have a cycle of order less than 6, then the robber can always hide from a single cop in that cycle. So I just want to illustrate this quickly with 4 cycle. So remember, we're just talking about 1 cop now. So this is where the localization game was initiated, was only played with a single cop, and the question was, can a single cop catch a robber? And then eventually it developed into this multi-probe game that we're actually looking at. So for a single cop, these are the 2 possibilities that can happen if the cop probes a vertex in the graph. It can either happen that we have a diagonal safe set, so that these 2 vertices, black vertices, have the same distance away from the probe vertex, or we can have an adjacent safe set. Might be that there is some cycle here at the bottom, and the probe vertex give the same distance for these 2 black vertices. So if the robber is located at this diagonal safe set, then it doesn't matter what the next probe is. The robber can move anywhere in the cycle from those 2 probe vertices. So he would be able to hide either on an adjacent safe set or on a diagonal safe set. So it doesn't matter where that probe is, he will always be able to hide. And this goes for small cycles of order 3, 4, and 5. And in fact, for most 6 cycles as well. There's just a few 6 cycles for which it doesn't hold. So it's only for graphs of the 7 and more that we can consider when 1 cop is sufficient. Now I want to move to specific graph classes. Firstly, to trees. And I must say, I think this is one of my favorite things about graph theory. You can say things that doesn't sound like maths. Can a robber hide from a cop in a tree? If I utter this sentence in a random conversation, no one will know that I'm talking about graph theory. That's fine. The answer to this question is sometimes, I have a little example here for you. Here's 2 trees. A robber can hide from a single cop in one of these trees. These trees are very similar. I don't know if you can see the difference, but there's only one difference there. This tree on the right-hand side has an extra leaf. That's all. So if you think about this intuitively, can a robber hide from a single cop in a tree? Well, my answer would be yes, if it's a very dense tree, he might get away with it in real life. Or a dense cop, one of those 2, but not really. So maybe intuitively you will think that if there's more leaves, like in the right-hand side, the robber would be able to hide in that tree. It is true, but it's not really because there's more leaves. It's because of this nice substructure that you can find in the tree. So yes, you can hide in the right-hand side and not in the left-hand side because we can see this red substructure. This work was done by Seeger in 2014, and she showed that this graph T33 is a hideout. So the robber can hide from a cop just by staying on this graph. He doesn't have to go anywhere else. A single cop can't catch him if this is present. I want to show you why. It's quite nice. What she did was to show that doesn't matter where the cop probes, the robber will either be able to have this red subset in the area where he can move to in the next step, or this green subset, or something that has the structure. So it might also be the two branches with C and D, as long as it's isomorphic to that structure. And how we show this and why this is true is when we start the game initially, we know that the area where the robber can move definitely contains both of these structures. So if we can show that if I start in one of them, I will always be back either in the red one or the green one, I have an escape route for my robber. So let's look at one of these cases, just to get a feel for this. If I start in the red case, so remember the robber can only be at vertices A, B, C, and D. So if the vertex E is the closest vertex to the probe vertex, then, and we just have to check one of the leaves, then C and D will have the same distance away from the probe vertex. And therefore, in the next round, the robber can be anywhere in these two branches of the graph, which looks like the green subset. If B is the closest, the same thing happens, just in a different part. C and D is will once again be a safe set, and it can move into something that looks like the green graph. And if A is the closest to the probe, then B, C, and D will be a safe set. But then the robber can move anywhere in here, and it will contain both the red and the green one. So if we start in the green set, doesn't matter where the cop probes, we will always either get back something that looks like the green or the red. So the cop can continually evade, the robber can continually evade the cop in this case. And similar arguments hold for the case where you start in the green one. So we can hide in this kind of tree. In fact, she characterized all kinds of trees in terms of the localization number and showed that it is one if and only if it does not contain this substructure in the tree. So from trees, there were some ideas about planar graphs, and it's interesting to say that planar graphs, for planar graphs, the localization number is unbounded, but for outer planar graphs, it is bounded from above by 2, similar to the tree. And if you don't know what the outer planar graph is, don't worry too much. There's a nice example. That, in fact, is a cactus graph, and you can see why. But the outer planar graph is a planar graph where all the vertices lie on the exterior region of the graph, which means that you will never find a vertex inside the cycle. All the vertices must be on the exterior region of this graph. You can have lots of edges inside these cycles, but just never a vertex. So when I saw this, I thought, oh, maybe we can see if we can extend Seeger's results and see if we can find which graphs are hideouts in an outer planar graph. But there are way too many cycles in an outer planar graph to start there. So we first venture to something easier, that it's a unicyclic graph, so a graph with just one cycle. And interestingly enough, the T33, that's a hideout in trees, is not always a hideout in a unicyclic graph. This specific example was given in that paper by Seeger. If we have a cycle that includes two leaves of the same branch of T33, then one cop can find the robber. And the reason for that is just that the cop can chase the robber into the cycle and then he can catch him. And that we can probe from the bottom here and make it easier to catch it. So it's a neatly written out way of doing this, but it's too long for tonight. Important thing is, in a unicyclic graph, a robber can't always hide on T33. But we've managed to show that it can almost always hide on T33. The only case where it does not happen is when we have the cycle between two leaves of the same branch, except for this case. I call it the reindeer graph. It looks like a reindeer. In this case, we have two T33s that's too close together. So if you see, those two are the two leaves of the one tree and of the other one. So they share a vertex with one another. And if they're this close together, then a cop can't hide or can hide again from a single cop. So all in all, what we found is so far, this is work that I'm doing with some students of mine over holiday work. So we found that places where it can hide on a unicyclic graph is when there is a copy of T33, as long as T33 does not contain, or as long as not all the T33s has a cycle on one of the leaves. If we have this corona graph, very timely. So if there's a corona, the cop won't find it. It's going to stay at home. And then the robber can also hide in this reindeer graph. We're busy looking at whether these are the only cases. Hopefully they are. I want to end with some open questions. So in this talk, we looked mainly at hideouts where we have only one cop. So we know where a robber can hide if there's a single cop. But what happens if we increase the cop? Can we find hideouts for more cops? It would be really interesting to see how that would look like. In terms of outer planar graphs, it would be super nice if we can characterize the unicyclic graphs in terms of their localization number and say this is what localization number 1 looks like, localization number 2 looks like. And then to see, we saw that there was a change from the hideouts from a tree to a unicyclic graphs. Maybe if we add more cycles, there will be more changes to these hideouts and we have to exclude more things. So it would be good to see if we can carry over these hideouts to outer planar graphs. And then finally, if it happens, we can characterize outer planar graphs. Then last thing, promise, is that of edge removal. So this is one of the things that I really like. I like to see what happens to parameters if we change a graph. I vaguely touched on vertex removal, but we can change the graph in many ways. And edge removal also poses a problem because it can both decrease and increase the localization number. So to see that it can decrease the localization number, it's very easy to show that the localization number of a 6 cycle is 2. And if we take away one of the edges, then the localization number of that path would become 1. So the removal of the edge decreases that localization number. On the other hand, if we consider that double house graph again, we saw that the localization number is 2. But if I take away that edge xv, then the localization number increased to 3. So the localization number can decrease and increase with the removal of an edge. So the type of questions you can ask is, what type of edges will decrease the localization number? What type of edges will increase the localization number? For the cycle, every single edge's removal will decrease the localization number. Do we have other graphs for which this is true, where any edge's removal will decrease the localization number or increase for that matter? So I really think I've just touched on a few subjects. There's a lot more that can be done in this field. So if you're interested, there's a whole bunch of stuff that you can go and read. Thank you.
Thank you so much, Riana. Thank you for the excellent talk. If you can, please join me to clap for Riana. I stop recording now and feel free to ask questions.